If phi of n is the least power for which a to the power k is congruent to 1 mod n, we say that a is a primitive root mod n. We showed that a primitive root had to exist mod 11, which gave us a way to construct a primitive root for any modulus. Or did it? Suppose n equal to pq plus 1 is prime, where p and q are prime. Then phi of n is pq, so any element A must have order 1, p, q, or pq. Now we know that x to the power pq congruent to 1 mod n is true for all x, so there must be pq solutions. If any of these are primitive roots, we're done. So let's assume there are some non-primitive roots. So consider x to the p congruent to 1 mod n. Since n is prime, this congruence has at most p solutions, so there are at most p values with order p. Likewise, the congruence x to the q congruent to 1 mod n has at most q solutions, so there are at most q values mod q. Since we're assuming there are some non-primitive roots, at least one of these congruences has a solution. But our next step requires that they both do. Is it possible only one of them has solutions? So there are n-1 pq values mod n distinct from 0. Of these, 1 is the only one with order 1, so there are n-2 values that could have order p, q, or pq. Suppose that only the first congruence has solutions. Since there are at most p solutions, which would include x equal to 1, so there are n-1 minus p, that's pq minus p, values mod n that don't have order p or order 1. And because p and q are assumed distinct, the least possible value occurs when p is 3 and q is 2. But even then, the right-hand side is, so there's at least 3 values that won't have order p. If any of these have order pq, we're done. Otherwise, at least one of these will have order q. So we know that our second congruence also has solutions. So let A be a value with order p, and B a value with order q. Since p and q are distinct primes, the greatest common divisor of p and q is 1, so that product AB must have order pq. And again, AB has to have order 1, p, q, or pq, but it can't have order p because if we find AB to the p we get, which can't be 1. If we find AB to the q we get, which can't be 1. And AB itself can't be 1 because if we raise it to the pth power we get, which can't be 1. And note that this is a constructive proof. It tells us how to find a primitive element. However, generalizing it is challenging. If n is a product of primes plus 1, then an element could have order, and we'd have to show that if non-primitive elements existed, then all of these would have solutions. So let's consider a different situation. Suppose n is p to the k plus 1, where p is prime, so phi of n is p to the k. We're still assuming n is itself prime. For example, suppose we're working mod 17. Phi of 17 will be 16, and as before, for all x to the power 16 must be congruent to 1 mod 17. And what makes this work is we can rewrite this as, so either x to the 8 is congruent to 1, or x to the 8 is not congruent to 1. If x to the 8 is congruent to 1, then x is order 8. Or is it? It could also be of any order that divides 8. So any solution to x to the 8 has to have order 1, 2, 4, or 8. And so there are at most 8 elements of these orders, and this leaves 17 minus the 0 element minus the 8 elements of order 1, 2, 4, or 8. That's 8 elements of order 16. This worked because n was a prime of the form 2 to the power k plus 1, so phi of n was 2 to the power k. The solutions to our congruence had at most 2 to the power k minus 1 solutions, which would include all elements of order less than 2 to the k. But since there are at most 2 to the power k minus 1 of these values, then there's n minus the 0 minus the 2 to the power k minus 1 values of order less than 2 to the k. That's 2 to the power k minus 1 values that must be of order 2 to the power k. Now, note that n equals 2 to the power k plus 1 will be prime for numbers like 5, 17, 257, and so on, so we have a method for finding primitive roots mod these numbers. For example, let's try to find a primitive root mod 17. Note that phi of 17 is 16, so we just need to find a value that isn't a solution to x to the 8th congruent to 1. And we find 2 to the 8th, well, that's 1. 3 to the 8th is 16, so 3 is not a solution to x to the 8th congruent to 1. So 3 does not have order 1, 2, 4, or 8, which means it must have order 16, and it's a primitive root.